In this movie, I'm going to show you how to draw a molecular orbital diagram for O2 and F2. To start, we're going to sketch the energies of the atomic orbitals. So number one, sketch the energy diagrams for the atomic orbitals of the free atoms. This is the diatomics. We'll label them X1 and X2. And for O2 and F2 will be in our valence shell will be the second energy level, so we'll have a 2s, a 2px, a 2pz, and 2py. And I like to sketch in the general shapes and orientations of those orbitals. Now these are just the valence orbitals. I'm not showing the lower lying orbitals because they're not involved in bonding. For our second atom, we're going to have the exact same orbitals because it's the same atom, and they'll be at the same energies. And here's a sketch of the relative shapes and orientations of those orbitals and the other atom. So this will give us a nice view of how those orbitals can interact to form bonding and antibonding interactions. In other words, which orbitals have symmetries that match. So again, take note that both sets of these atomic orbitals are at the same energy. And this is because this is for a homonuclear molecule. In other words, they're the same atoms, so these two atoms have the same beginning atomic orbital energies. And what this means is that each atom's atomic orbitals will contribute equally to the bonding and antibonding molecular orbitals. We'll start by showing the interaction between the two s. So begin sketching the molecular orbitals that are going to be produced from the atomic orbitals of like energy and symmetry. And remember that the number of molecular orbitals should equal the number of atomic orbitals. So the s orbitals interact to form a bonding interaction, which will be sigma g, and an antibonding subtraction of those two s orbitals produces the antibonding sigma orbital, and we'll sketch in the dotted lines. Next we have head-on overlap of our two pz orbitals. The bonding looks like this. So that'll be a sigma bonding orbital. And then the antibonding orbital, subtraction of those two orbitals, like so, produces the sigma antibonding orbital from the two pz overlaps. And there's the dotted lines to show where those MOs came from. Next we have the pi interactions. So draw those in. We have a side-on overlap of the two px orbitals that can be used to approximate the bonding, and then here the antibonding orbitals. So the bottom one is the bonding, showing the positive overlap between those, and then the antibonding pi orbital. And of course the 2py interact, they are exactly perpendicular to the 2px, interact in the same side-on fashion, producing a pi bonding and a pi antibonding interaction. So there's a diagram. Now all we have to do is to fill in our electrons for whatever molecule we happen to be working with. This will also work for ions of O2 and F2. But let's just show the demonstration for F2. So for F2, each fluorine has 7 electrons. Let's fill those in to the atomic orbitals. And of course, start at low energy, only pair up when you have to. So we're following Hund's rule of maximum multiplicity for each side. So we pair up when we have to. There's the electrons in our atomic orbitals. So we have a total of 14 electrons in the valence shell that will contribute to our molecular orbital. We'll fill those in, starting at the low energy and moving up. And I'm going to first add them in singly, parallel, and then only pair up when I have to. And again, so this is the completed diagram. Notice there's no unpaired electrons. This is a diamagnetic molecule. We can calculate the bond order, which is equal to the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding orbitals divided by 2. So that's going to be bonding orbitals. We have 8 total electrons in bonding orbitals and 6 electrons in antibonding orbitals divided by 2, and so we have a bond order of 1. And this matches the Lewis structure, which also shows a bond order of 1.